Welcome, everybody. Thank you for coming to my lecture this morning. I'm here to talk a little about artificial intelligence and machine learning mostly. I do neuroscience research up at Stony Brook University in New York. I'm also a computational neuroscientist and a wannabe physicist. And our lab that I work in has a dual affiliation, Stony Brook Biomedical Engineering and Harvard Medical School. And our work is primarily applying computational methods to understanding the brain. So very excited about both. I hope you're also excited about these things. And I will try to end on time today instead of the grand academic tradition of disregarding time limits. I have nothing to disclose either. So seeing as how we're going to use this as an introduction to machine learning theory by way of the brain, what we'll want to do is start with some basics about neuroscience. And so that's important because in the brain, it's very optimized for learning and thinking, and so oftentimes form dictates function and the other way around. The brain is made up of cells called neurons at the microscopic level, and all of these neurons connect with each other. There are about 80 to 100 billion of them. They have a central bit here called a soma, or a cell body, and they have dendrites coming off of that. And all of these dendrites connect with other cells, and that's fairly important for reasons which we'll examine in a second. These are actual neurons. They're stained, collected from a real brain. And it's a pretty cool image. It's kind of chaotic, so I don't know if you can quite tell what's going on, but you can see branching dendrites, and you can see your cell body. And the connections are there. They're just very small. One interesting thing about the synapse is that it's not actually a connection so much as an empty space. And that's the defining characteristic of your synapse. And it's an important thing to study because a lot of interesting things happen at the synapse. Among them is information transmission in the brain. And you can see this is another slightly more realistic drawing of two neurons. You can see where the synapse is relative to the other things and how the dendrites in a receiving neuron connect with an incoming neuron in order to create these synapses. So like I said, the synapse is responsible for this transmission of electricity, and that defines information motility in the brain. So if you have this traveling signal, you have a small problem when it gets to the end of the neuron, which is that there's this empty space. The brain gets around this empty space by releasing a flood of electrically charged ions that recreates the current in the next neuron, and it travels through and it goes on its way. Now, this information motility contributes to this concept we call Hebbian learning. Hebbian learning says that when two neurons activate simultaneously, they grow stronger between themselves. And the opposite is true as well. When they activate separately, they weaken. This is also called synaptic plasticity, which you may have heard of. And it's an important thing because it helps us learn things. This is an equation for neural output, so we can look at how inputs come together. They get multiplied by that weight that we look at in Hebbian learning, and they all get summed together, and we get one output. So this relationship that we've defined here is subject to Hebbian learning rules, which say that when we get something that activates simultaneously, this weight will increase. So equation 2, if we have this generalized framework for weight update in a synapse, we can say that the next weight is equal to the current weight plus some change, and we can fill in the change with our Hebbian learning rule. And so in this case, I've chosen a rule called Oya's rule, which isn't really important. It's just a form of stable Hebbian learning. And it says that the next weight is dependent on the current weight plus this change, which you can see is dependent on the input and the output. So you encode that simultaneous activation there. And you can index your set with multiple neurons if you want. The last thing that is kind of important about Hebbian learning is that it's an automatic process. Optimization in Hebbian brains is automatic. If we decide to increase our synaptic weight, it's due solely to the activity of those neurons. And those neurons fire because they encode some sort of stimulus response. So if there's a response that we really like, say A fires B, and that represents pulling your hand out of a fire. That's a response that we really like in response to that stimulus. And so the brain says, let's do this more often. And the pathway becomes stronger because they fire together more often, becomes easier to perform. And so that's how we encode learning in Hebbian synapses. It's based on what we have learned is a good response to the environment. In practice, this is something called long-term potentiation, Hebbian learning is responsible for that. It's a mechanism for learning. It makes two synapses stronger and makes the circuit of communication between the two. And so if we consider an environmental cue as being represented by a Hebbian synapse and the response to that also being represented there, it makes sense. It's analogous to Pavlovian conditioning. A bell rings and you get fed, and so you associate that with that, and the synapse increases its strength. So having laid some groundwork about cells and networks and connections, we can switch gears and discuss machine learning. Knowing that there are two types of neural networks, things that are in our heads, biological neural networks and artificial neural networks are also a thing, we can apply these concepts from real neurons to computational neurons. Neural networks are statistical models which identify patterns, and so they need to learn things about what they're looking at, about the data set that they're dealing with. Structurally, they're very similar to real neurons. They have a number of inputs that get weighted and all go towards an output. So you can see this relationship is preserved in artificial neural networks, and your weights are changed proportionally to correlated input and output activity, just like in biological brains. Right? Machine learning algorithms are also subject to Hebbian learning rules, which is kind of cool because that is one of the substrates of learning, and that's what makes learning about data sets possible. Without this changing of weights, your algorithm will probably not work very well. And so you can say that's your set of inputs, and it's going into an output. So, like I said, just like the brain, an algorithm can follow Hebbian learning. You increase synaptic weight if a parent neuron fires just before a child neuron, and you decrease it otherwise. And weights are the pattern of information that's most useful from an input. It's what the receiving neuron cares about. Just like a Hebbian synapse, it encodes the best possible response to a situation. And Hebbian learning is great. It's considered an unsupervised algorithm, so it doesn't require training to get where it needs to go. It works in a lot of cases. Hebbian learning, however, does have its limitations. And in the brain, we get around this by having this psychological feedback mechanism. We know what is a good response to a stimulus and what isn't. Neural networks don't necessarily have that, so we need to add in an element of optimization. And the way we do that is by training. We look at minimizing an error between a training data set and a produced output. That's a very powerful tool. But it leads to the question, does the brain do error minimization? So we mentioned there's this psychological feedback mechanism. And in the brain, do we do training? Do we do error minimization? Which is an important question. And we find that we do. In the brain, there is a sort of a training regime where we refine what our neurons do and we consider something useful, just like training data in a neural network. And the methods are very similar. There are a couple of key differences, right? And so to investigate that, we've got to revisit the brain, but as a processor. And as we move away from Hebb's original rule, right, we get a little less concrete and a little more theoretical, a little less evidence-driven. But experimentalists are no fun, so we move on ahead anyway. And so to look at machine learning, we do want to look at what does error correction and training data look like in the brain. In order to answer that, we need to examine energy. And we need to know that energy forms a really good supporting column in our understanding of the universe. And so it applies to the generation of thoughts and brain activity as well. We can skip parts of this. Just that there's this idea called free energy. It was discovered by a guy called Hermann von Helmholtz. And he drew an equivalence between something called free energy and something called entropy. And entropy is a very broad concept. It characterizes a lot of things, including information uncertainty, information quantity, the difference between two distributions. It can also mean randomness or disorder. And so that's quite useful for us because it's such a broad category that's united by one concept. And Helmholtz also studied perception, which is kind of cool, kind of a coincidence, but he never united his ideas, which is unfortunate. Luckily, this guy called Carl Friston came along, and in 2006 he did unite the two by applying studies of energy to studies of perception in the brain. He comes up with this idea called the free energy principle, which is a very powerful but very complicated idea, which I have maybe highlighted here. It's a little tough to wrap your head around. However, it is important to discuss because it is a powerful concept. As a psychological model for learning and perception, the free energy principle states that we avoid surprise by making good predictions. So in order to minimize error, or the difference between our idea of something, what we have learned, and the reality that we're looking at, we try and update our hypotheses about something. If I stick my hand into a fire with the internal idea that it won't hurt, and then I'm wrong and it hurts a lot, my model is different from reality, so I update it by saying, hey, maybe don't do that, that'll hurt. And that gives you some idea of the maths behind it. It's not pretty. Well, I think it's very pretty, but you probably won't. And I do want everyone to get to lunch on time, so we're not going to go into this, but you can get an idea of the actual under-the-hood complexity of free energy here. If we revisit this slide, we can see this application. Entropy measures disorder in the brain, and the brain tries to stay very ordered because that's how we maintain our ideas about the environment and prevent our brain from kind of decaying into chaos. And so we minimize our free energy. Friston lays out this world where we can look at what's around us and learn things based simply on what we look at. We unconsciously realize we're wrong, and then we rethink it. And he also said cortical responses are the brain's attempt to minimize free energy, and that learning emerges from changes in synaptic efficacy that minimize the free energy in the brain. So he utilizes plasticity to explain this change in representation, this updated learning of our environment. So we can use this thing called Bayesian statistics to model what we learn about something and how we update our ideas about something. So if we have the probability of M, our internal model, given O, a new observation, we want to test how accurate our model is. So we find the percent chance that our internal model is still correct given some entirely new observation. And that's based on the probability that we would see this observation at all if our model were 100% correct. It's also dependent on the probability our model is correct at all. So if we're wildly off base, this will be near zero. Or the probability that we see that observation at all, so we can eliminate outliers, we can normalize it against that. And using this, we find that we can update our internal models about something. And because we store these models in our memory, and because synapses are responsible for what we learn about the environment through conditioning, we find that we can see these models, we can see representations of the data around us in physical neurons. We can change our synapses in a Hebbian style in order to minimize free energy, because you have free energy going into physical representations of data, because that's how we store things. So we can use Hebbian adjustment to minimize free energy, and that's based on this relationship. What we do is, because we can't go in and explicitly change our weights. That's not what Hebbian learning says. Hebbian learning says our weights change based on our inputs and our outputs. What we do instead is we change our neural output, because if our neural output changes, we can't change our inputs, they already exist. If our neural outputs change, then our weights will change proportionally. And so we minimize free energy by updating our perception of the world. And we update our perception of the world by changing the way we use our neural synapses and generate neural activity. And so if we build a model of our environment characterized by a couple of variables, we see what happens when we perceive something is we try to recreate this thing that we've seen based on our model of the world in our head. And we need to infer some of these variables, like an actual data point V, based on our observation of the world. And so we have an expected data, and we have a function that maps that. Say we're looking at a 3D object. We can only see the surface of it, and we're trying to infer its 3D size based on a light map. We have an observation for light intensity, and we have a function that says, hey, if you see a shadow around a corner, that's probably a rectangle. And so we can infer a data point based on what the actual data is and based on our observation. And so we use that in a way to model our environment. If we have this function, great, we can theoretically figure out what shape anything is based on our prior experiences. So we come up with all of these expected distributions of these variables, and we say we only want our relevant prior experiences, because if we're looking at some 3D shape, we don't want to know anything about sticking your hand in fire. We don't really care about that anymore. So we pick a distribution of only the things that we've seen about light on a 3D object, and that's encoded by this variable phi. So this model of perception is subject really to two errors. One is the new distribution that we've chosen, because if we chose the wrong prior model, then our prediction will be wildly off base. And also our error in our prediction. Because if we say we see a shadow around a corner, and that's going to be a rectangle, but the actual shape is a trapezoid, then we need to update our model and say, well, it can also be both of these things. And like we went over that these models are reproduced in neurons, because that's how we represent data in the brain. We can assign all of these variables to real things in the brain. For example, our input is our sensory observation, U, and we have error terms in neural output, which are also states on neurons, and we have memories or learning in the form of noise and our predicted model, etc. So that's how we are assigning what we look at and what we think to the brain. And then we can use these equations to minimize that error. And like I said, we can't go in and change our weights explicitly. What we have to do first is change our outputs and change our representation of the world in order to change that weight. So you have reproduced, right? We've put Heb into this mess, and we've said that the state of the neuron will change the connections between it. We won't change connections explicitly. And at this point, I'm sure you're thinking, I never want to hear the words free or energy again. And that's okay, because if you're a little confused, so are a lot of people. But what we need to take away from this is not really anything about that. It's only that the way free energy works is we have a model of the universe, and we want to go in and update it relevant to our new observations. We want to say, if I observe something that doesn't agree with my model, how wrong is my model? Is it wrong enough to be worth changing? And then when we change it, how do we want to change it to re-encode these new observations and these new sets between whatever we look at? So with that, we can segue into machine learning, because in machine learning, we are trying to create a model for something. We're giving a machine learning algorithm a data set, and we're trying to find something to explain what we see in that data set, and then explain other data. What we do is we pass in some training data, and training data is your ground truth. You have an input, a known input, and you have a known output. And so we can actually verify that our model works based on this ground truth. We can pass in our training data, we can get a produced output, and we can compare it to the known output. And that's the same as what the brain does when it perceives a data set about the environment it's in. It comes up with this internal model of what is going on around me, and then it tries and updates it, comparing it to the reality of what's actually going on. And that's how we actually calibrate what we're looking at and how we're processing data within our brain. So what we do is we come up with this actual model that maps an input to an output. So we have a given input, and we map it to a given output, but we also want it to represent other forms of data. So what we have is a function that maps older given outputs from older given inputs, subject to the condition that the probability that your model includes stuff from other distributions is near 1. So all this says is we look at some training data, and we come up with a function that maps an input to an output. We come up with some function explaining how the data gets transformed to get an output. But in order, that just explains the data, it finds patterns. In order to explain future data and make predictions, our model needs to actually be good. So we have this Bayesian probability that our function is still correct given new observations. And that's how we make predictions about things and extend our model to other use cases. So I'll skip over putting machine learning into a free energy architecture. It can theoretically be done, but I don't really think it's worth doing necessarily right now. Instead, what I'll say is machine learning practices error minimization just like the brain does. And it does this both dependent and independent of Hebbian rules. So independently would be something like back propagation, if any of you are familiar with that, where back propagation goes in and changes the weights until there's zero error between our training data and our given data. However, we're more interested in Hebbian rules because that's the whole talk, but also because local computation is very powerful. And we see that in the brain, and we see how it's flexible enough to really represent very complex data. So we're going to look at, if we recall equation 3, where we have this generalized thing for synaptic update. We're going to look at trying to put this into a free energy framework or some sort of Bayesian modeling framework, something like that. And we can plug in a new Hebbian rule, something a little different that satisfies our new constraints. That's called the delta rule. There are a lot of different Hebbian learning algorithms, and there are a few that also do error minimization. This is the one that I just chose because I kind of liked it. In this case, we've used the delta rule. It says that the change in your model, the change in your synaptic weights in your model, is going to be related to your given outputs versus your actual produced output. And what it says is if I've inferred a function that doesn't yield my new output, doesn't yield an accurate output, then my model is wrong. The probability that my model is correct given this new observation is much less than 1 because I haven't produced the new observation. So my model is wrong, so I want to change my model such that the intended output is more close to what I actually get. So I want to minimize the difference between what I make and what I've actually produced. And so I go in and I change the function based on that. And then that's kind of what we've got with that. It's easy to get lost in the minutiae, and if you were neuroscientists, I'd say unifying models of perception and learning would be riveting, but most of you are engineers or data scientists, stuff like that. Most of you are applications people. So takeaway for you will be probably zooming way out and saying, the human brain is really, really good at identifying patterns and about learning things. And what makes the brain so good at this is combining error minimization and synaptic flexibility. And that represents information and then computes on it in the best way possible. And this is a very powerful tool, and that's how the brain is such a good processor and how it can register and learn about such complex data points. And machine learning models can use this to a large extent and can make use of error minimization and synaptic plasticity, as well as other things we haven't even really touched on, like hierarchical structure and input integration, memory, and stuff like that. But the parallels between one and the other are no coincidence. That's the important point. These mechanisms are what allows learning statistical models to explain data in both the brain and machine learning. And AI extends these models to explain other data, making powerful predictions, just like we learn functions that are not just relevant to what we're learning about right now, but extend to other scenarios as well. And the brain is flexible enough to function in other scenarios. And we are flexible as people in other scenarios. And we have some ideas for the future about what other things we can bring in and how neuroscience will continue to drive AI and how AI will continue to drive neuroscience, and whether neuroscience can ever lead to more complex systems. I try to stay away from the C word, consciousness, because it's very ill formulated, and so it's very difficult to study. But there have been proposals that free energy can really help us with generative models, and generative models in turn can help us model consciousness in the brain and eventually perhaps apply one to the other. It's a possibility. It's way far in the future, but it's something that is maybe exciting. There are a couple of papers that I referred to during the process of putting this together, in order of appearance mostly. They make for good further reading if you're interested. And I know I went a little quickly, and we've got some time left. So if you want me to go back to something, I'd be happy to re-explain something, because I did go very fast through a lot of the Bayesian stuff and the free energy stuff, and that can be difficult. But otherwise, that's pretty much it. In the last few minutes, I can take lingering questions, if you have further questions. Yeah?
So, what, in your opinion, is the scale of difference between the complexity of a neural network into a computer and the complexity of networks in your brain? Do you have an idea of that?
In neural networks on computers, just by virtue of not having a lot of computational power, they can be quite large. Sometimes they can be hundreds or thousands of layers of inputs and outputs. And that is very effective. However, the brain is orders of magnitude higher than that. Like I said, there are 80 to 100 billion neurons in the brain, and all of them connect with each other. There are uncountably large synapses between those neurons, and so it's very difficult to recreate that in a computer. So one day, maybe we'll be able to get there. And especially when you look at the brain, it's mostly regional. The brain is hierarchical in a couple of different scales. You've got hierarchies of passing inputs and outputs from one sensory region to another. Like you have 5 visual cortices, for example, and they all process visual stimuli together. And so that's very powerful because you have so many weights and so many opportunities to do computations. That's very hard, like I said, to produce in artificial neural networks simply because of the scale of it. Eventually, one day, yeah, maybe we'll get there. Yeah?
I have a question. You might want to repeat it. I don't know if the camera picks it up. But you've shown Havian learning, basically,
Mm-hmm.
at the beginning of it. Hebb is from last century. I think he's like somewhere in the 50s. This is very popular.
Yeah, yeah.
Yes, 56. So it's kind of old, but his ideas keep on remaining. What is, and you've shown a very good overview up until the point of showing the short presentation. But can you talk about what's developed now that's on top of it or better than this? A little bit about that. But
We find that Hebb's rules stick around. Sorry?
repeat the question shortly for the camera.
He asked, what have we found that is similar or maybe different from Hebbian learning that allows us to improve on our knowledge of synapses and neural activity today? What are some of the differences in our base of knowledge today? And we find that, you know, Hebb's rules stick around. Experimentally, they were validated back then, and they do stick around today. We find, however, that there are certain things about communication in the brain that are less related to Hebb's rules and are slightly interesting. So for example, there are neurons in which electricity can jump across the synapse. And so it's possible that we miss some of the long-term potentiation in that case, although there is a lot of evidence for long-term potentiation across the brain. It's just not necessarily always based on neurotransmitters and receptors. Sometimes it's based on just electricity jumping the gap. In terms of neural connectivity and neural connections, we find that there's a lot of connectivity across larger regions than just neural cells. For example, there are connections in between different brain regions. The region of the frontal cortex is mostly responsible for higher order thinking versus something like the parietal lobe or even the temporal lobe. The temporal lobe is responsible for auditory stimuli. And there's connectivity, there's information transfer between those two regions, which is not necessarily related to Hebbian learning because there's no synapse there. It's mediated by a different type of neuron called axons, which are included in most neurons, but in this case, they are much longer. They're white matter tracts, and so the synapses there are few and far between because they're basically very long cables. Yeah. Okay, if there are no other questions, yeah.
Is it completely unknown how many synapses there are? In the brain?
There have been estimates, but none of them are terribly reliable because they're so difficult to measure, you know.
Because they're so tiny.
Yeah,
Small.
very small. Mm-hmm. Yeah.
If we look at the life cycle of the brain, as an infant, you're able to learn very easily, and it's much easier as adults. It becomes harder and takes longer to, like, say, pick up a language. So if we develop ML models, can we see a similar behavior in our computing aspect as well?
Part of the loss of synaptic plasticity in the brain is due to the energy constraint in the brain. So as we get older, our neurons get more resistant to things like insulin, which results in an inability to sustain life processes. And so we have less energy to work with, and we can do less with this synaptic plasticity. And so that's part of the reason why we lose that plasticity in adults and we still have it as children, simply because our brain cells are aging. If we tried to recreate that in a neural network, I'm not sure what it would look like. We would have to start with something that learned very effectively, because the way that humans behave, we do have those prior models, which we're able to learn earlier in our lives. And then if we tried to recreate the drop-off in synaptic learning, we could have something that decreased the ability to change those weights, and it would probably begin to learn less effectively. And that's why it's so difficult to learn a new language as an adult, for example. So we would probably find that model would start making bad predictions, and it would continue to make bad predictions instead of updating it as a younger model might be able to. Yeah?
You talked about able to model the consciousness sometimes in the future.
Yeah.
What would be the benefit? How would it translate into an ML deep learning model?
It probably wouldn't. There would probably be not much benefit from a data analysis standpoint to modeling consciousness, although conscious AI would be able to apply itself in other fields for sure. Things like, sorry?
Skynet?
Yeah, maybe. But we find in other fields like the health field, we find that one of the big stumbling blocks to using AI is lacking empathy. I wouldn't want a robot telling me I have 6 months to live, for example. So perhaps a conscious AI would outperform other AI in that sense. But again, consciousness is very ill-formulated as a problem, and so it's difficult to talk about solutions to it. You know?
Understood. Thank you.
All right, if that's it, then I'll leave this up here and I'll let you guys go, pretty much.